Hello, welcome to the Danish Academic Society of Robotics webinar on robotic science. I'm Henrik Christensen. I'm normally a professor at UC San Diego. I'm a Dane by birth and by training. Got my education at Aalborg University and is still very much tied into the Danish robotics community. I'm sure you know about Danish robots. You know, we see them from Universal Robots, from Mir, from all sorts of places. So there's a lot of awareness about how great Denmark is at actually making robots. There's maybe a little bit less awareness of what's going on in the academic community. So we're using this seminar series to generate more awareness of what's going on. And we're doing this by traveling around in Denmark. We have 4 seminars. We had one about a month ago at Southern Danish University in Odense. Today we're going to Aalborg University. And then in a month, we'll go to the Danish Technical University in Lyngby. And finally, we will finish off just before Christmas with a seminar series about why is Denmark so good at doing translation of robotics technology and making sure that we actually have economic impact. As I said, this is the second seminar. We're going to Aalborg, very northern part of Denmark. It's my alma mater. Aalborg University is very famous for doing problem-based education. It was one of sort of the first universities that really sort of picked up problem-based education quite some time ago by now. They're also well known in robotics, and they have a very broad portfolio of robotics across manufacturing technologies, healthcare, arts, and also sort of core technologies on human-robot interaction. And today you're going to get a tour of all of these different, and we will get sort of a very nice view of what's going on. My local host or co-host today is Thomas Bach. Thomas is a professor in the Department of Electronic Systems. He's also the chair of the department. So Thomas, I'm handing it over to you.
Thank you very much, Henrik. And thank you for the introduction. And thank you to all of you who are joining today. We do appreciate you taking the time to listen to our research at Aalborg University. This is the second episode of the webinar series, and my job today is to guide you through the next hour and 20 minutes. As Henrik said, my name is Thomas Bach, and I'm a professor and head of the Department of Electronic Systems. I'm also chairing our organization called Aalborg Robotics that collects all the competencies within the robotics area at Aalborg University in a kind of a center structure. So today we are visiting Aalborg, and I have put in a few slides here. Aalborg University is in the northern part of Denmark with the main campus in Aalborg, which is the green marking here. Then there's a campus in Esbjerg and one in Copenhagen. About 24,000 students, and of those 840 are PhD students. We are very proud of, as a university, of the way we engage with society around us. We have constantly voted as the best university to collaborate with in Denmark for industry. We are also proud of our learning model, which is, as mentioned by Henrik, it's called problem-based learning, and it gives students problems to work with, and they do that through projects. And each semester they hand in a project, and then they are evaluated based on that. We also value interdisciplinarity, and today you are going to see an example of that as we have presentations that are inspired by problems in engineering, problems in medicine, and problems in art. The presentations you see today, they are from our initiative called a center called Aalborg Robotics, and Aalborg Robotics runs a bachelor and master science program with about 200 students. We collaborate across 4 faculties within the university, 8 departments, and in total there's about 35 professors and PhD students. There's a website there, robotics AAU.dk, and you can find more links on that site that gives you an insight into the different areas of robotics at Aalborg University. Some of them are given here. Okay, so before we start, I have a practical note. We have today 4 presentations, and if the presentation leads to questions, you need to post those questions, and now I am a little bit unsure where, and somebody who is handling the technical part here maybe can tell me where.
Yes,
Where do you...
of course, in the chat.
In the chat. Okay, so you post a question in the chat, and then after each presentation, I will try to I will put the questions to the teams that are presenting, and then we will see if we can get some answers. Let's go into the program. So today we start with a presentation on rehabilitation robotics. Then we have a presentation on advanced industrial robotics, a presentation in robots in the art, and finally on human-robot interaction. And then after that, I will come back together with Henrik and round off the webinar for today. So let me move on to first presentation, and that is Lotte Struijk, who will take over the screen now.
Thank you, Thomas. Now we will present the Rehabilitation Engineering and Robotics Lab. My name is Lotte Andreasen Struijk, and I am an associate professor at Aalborg University. Here I am leading the Rehabilitation Engineering and Robotics Laboratory, where we study how robots can help paralyzed individuals. About 5 million people live with paralysis, and this can be caused, for example, by a stroke or a spinal cord injury or a disease like ALS. Robotics has a great potential to help individuals that are paralyzed, but it's facing a paradox. The higher degree of disability, the higher is the gain, but the harder it is to control the robots. So our aim is to solve this challenge. To do this, we perform research on assistive robotic manipulators, both in nearby and remote settings. We develop new exoskeletons based on size, space, pathology, and user requirements. And we research on different control methods, for example, tongue control, muscle control, brain control, and we combine these control methods into hybrid systems. We use intelligence and semi-automation with a special focus on shared control, and we test our systems both in able-bodied individuals but also in individuals with paralysis. We collaborate with industry and clinicians and with the users to create useful solutions, and we use the nearby facilities for innovation to transform our research into available products. In the following, we will present 3 different projects. The first one is the Exotic project, where 4 PhD students and a postdoc collaborate to create an intelligent tongue control exoskeleton. The second project is the Multi-Rob project, which is supported by the Danish Research Council, and there 2 PhD students and a postdoc work together to create brain control, muscle control, and tongue control of an assistive manipulator, and to combine these control systems into hybrid systems. The last project is about brain control of an exoskeleton. So the first project we will introduce is the Exotic project. Here 4 departments work together to create a novel 5-DOF exoskeleton arm, which is semi-automatic and controlled by the tongue using the 9-DOF iTongue control system developed in this lab. The design of the exoskeleton is based on interviews with users paralyzed from the neck and down, and the users prioritized drinking and eating over a longer time, for example snacking, to avoid repeatedly having to ask for help. In addition, in the design, we included a shoulder doff reduction due to user requirements related to aesthetics and the limited space while sitting in a powered wheelchair. We used biomechanical modeling to assure that the exoskeleton still had the desired workspace.
The exotic exoskeleton relies on a rigid structure driven by small motors located along the length of the exoskeleton, together with a soft exoskeleton glove. In total, there are 5 degrees of freedom, including hand opening and closing. The upper arm rotation and wrist joints use a relatively special joint based on a semicircular guide design that twists the arm and allows for a more compact design, as shown in the video. For this exoskeleton, ergonomics was an important factor, as individuals with complete paralysis are prone to exhibit an autonomic response to pressure and irritation applied to the skin. Therefore, the exoskeleton has a soft attachment to the arm. As such, the arm is simply carried by 3 ergonomic braces located along the arm. The first problem you encounter when developing assistive technology for individuals with complete bodily paralysis is that they cannot use a standard interface technology like a joystick. Therefore, our group developed a wireless tongue control interface some years ago. The interface looks like a pallet brace and is put in the roof of the mouth. The bottom surface of the device can sense the position of ferromagnetic materials, like a tongue piercing, which is exactly how we command this interface. 18 tiny coils are embedded in the brace that detect whether a ferromagnetic material is in the vicinity of the coil. In practice, this enables individuals with complete bodily paralysis to fully control 9 degrees of freedom directly and continuously in an invisible manner. Using the weighted average of neighboring sensors, we can use this interface to simulate a joystick-like control, as shown in the video. While the tongue interface is already a great and efficient interfacing device, simultaneous control of the 3D position of the end effector is infeasible using a 2D interface. To overcome this and make the controls even more efficient, we have added a semi-autonomous control scheme through computer vision algorithms. By detecting the object of interest, we can guide the end effector through a control blending scheme by mixing the user control and predictions of the computer vision algorithm. Through this control scheme, the user is always in control, but the movement is simply aided by the computer vision to generate a smooth trajectory to the object. Our exoskeleton relies on MoveIt and the ROS backend for our software controls, and motor control is provided by EPOS4 CAN bus-enabled controllers from Maxon Motors. This is the first proof of concept tongue-controlled exoskeleton which has the potential to empower individuals with complete bodily paralysis to become more independent.
Thank you, Mikkel. And now Rasmus and Ausgedur will present the Multi-Rob project.
Within the Multi-Rob group, we work on providing control of an external robotic arm that can be used by individuals with ALS. The disease causes progressive paralysis of all voluntary muscles, which results in an increasing need of assistance but also a decreasing capability of control. In early stages, it will be possible to provide control through EMG. Then a tongue control interface can be used until the very last stages, where it is only possible to use a brain control interface.
When an ALS individual has lost the ability to use the muscles for control of their assistive devices, the next step, in order to retain control and remain independent, is to use the tongue. We are therefore working on a solution that should work in a remote setting to make the individual more self-supportive, for example when lying in bed. The solution contains an electric wheelchair, an assistive robotic manipulator, a tongue controller, visual feedback using multiple cameras, and wireless communication. The iTongue data is interpreted as a command for either the wheelchair or robot and sent to a computer on the wheelchair with the help of Wi-Fi and ROS. Visual feedback from the camera placed on the wheelchair's headrest and on the robot's end effector allows the user to take control from a remote location.
In later stages of the disease, ALS also affect the tongue muscles, making the tongue functionality inadequate to fully utilize the tongue control. We are therefore designing a brain control interface that allows manual control of the robotic arm. Each control command is presented to the user as frequency-specific blinking areas on a computer monitor. When the user then focuses their gaze on a blinking area, their brain signals will induce steady-state, visually invoked potentials that can be measured and classified to determine which blinking frequency and thus control command they focused on. Still, a brain control interface will perform much worse compared to the tongue control. We are therefore also designing a hybrid tongue-brain control interface that combine remaining tongue functionalities with brain signals. This will prolong the use of the reliable and fast tongue control while prepare the user for the eventual necessary full brain control interface.
Thank you. And now Ms. Jochum will present BCI control of wrist exos.
Stroke is the most common cause of acquired disability, and it affects 33 million people per year. 80% of the survivors suffer from movement disability, and even after rehabilitation, more than 50% require assistance in the activities of daily living. This is primarily because the patients are not training enough and due to inadequate rehabilitation techniques. The rehabilitation with a therapist is considered as the gold standard, and the training consists of therapist-assisted repetitive movements of the joints. Unfortunately, the therapist has very limited time with the patient, but many of the movement types that are performed can be performed by an exoskeleton, which allows the patient to continue effective training without a therapist. There is a risk, though, that the patient let the exoskeleton perform the movement passively, and it is crucial that the patient attempts to perform the movement. To ensure that the patient attempts to perform the movement, a brain-computer interface, or BCI, can be used to trigger the exoskeleton, so it only moves when the patient attempts to move it. This BCI continuously records brain activity and processes it in real time using different types of filters and pattern recognition techniques. Once the BCI detects that there is an intention to move, a trigger is sent to the exoskeleton, which then executes the movement. In our lab, we have worked with this approach for several years, and we are currently looking into developing cost-effective approaches that can be used in rehabilitation clinics and in home settings. This exoskeleton is 3D printed with a linear actuator, which performs extension of the wrist, and is controlled using imagined movements, which are picked up by the BCI through an Arduino.
Thank you very much for listening.
Okay, so thank you very much to the rehabilitation team. I have, if any of you listening on this have a question, please put it in the chat function. I do have a question myself, so I think I will post that to the team. Could you sort of give us an idea, what are the main scientific challenges you are currently working on in order to bring these exos out into the to use?
Thank you, Thomas. The main challenges when we combine exos with health has to do with, for example, aesthetics, that the users feel that the exo has a nice design. It's also the size of the exo, that they feel they can use it at home, bring it at home. And in that relation, also the powering is important. So these are the things, and then there are the challenge in controlling it. And in future, I think we will be using much more intelligence and to improve these issues.
Any idea how you can bring the weight of these exos down? Because you need a certain moment generated by the exo, I'm guessing, and that takes a certain motor, a certain size. So are you exploring any ideas on how to bring the weight down?
Yes, we are also looking on the construction itself. We are looking into soft exo designs and hybrid designs, and further looking into different materials. It could be carbon-based materials instead of metal-based materials.
Okay, so thank you. I have one more question that just comes to my mind. Is on those the brain-computer interfaces. I mean, that would be great to have such an interface so people can see what you think before you even know yourself. But is that actually the case? Is there a significant time delay in generating responses from a BCI?
When we're talking about re-establishing movements, then we can actually predict movements before they occur. If we actually were able to execute them, or if the patients were able to execute them, we can predict it approximately between 500 to 200 milliseconds before the movement. So there's not really a delay from that side. And then the delay will come when actually performing the movement with the exoskeleton. So it is a very fast way to trigger the exoskeleton. Of course, when we are predicting when they want to perform a movement, we can only do it with a limited accuracy. So we are in the range of approximately 80% correct detections of simple movements. And then if we switch to another control signal, for instance, the flashing lights on the screen, then we can obtain much higher accuracies. But again, there will be a larger delay, but that would be in the range of maybe 1 to 2 seconds.
Okay, so now there's a question from one of the participants here, and that is, this is Gabor Sibik, who asks, today the user controls the end of the exoskeleton, the arm. Why not control the objectives, the task of the arm?
That could also be an interesting feature to look into. And this is definitely also the fields that we will look into, different ways of controlling the exo, and also to try to integrate more natural motions, and that we can do by using biomechanical modeling also. So yes, it would be a good idea to look into the control scheme also.
Okay, I think that completes the rehabilitation robotics, and thank you very much to the team. I suggest we move on. So if you give up control of the screen, then we move up onto advanced industrial robotics and the next presentation.
Yes, well, thank you very much, Thomas. I'm Ole Madsen, and I'm very happy to have this chance to give an introduction to the Smart Production Lab. We have also made 4 small videos we'd like to share with you. 1 video giving you an overview of the lab, and then 3 videos where we dig a little bit deeper in some of the research areas. So Simon, if you would start the video, please.
My name is Ole Madsen. I'm a professor here at Aalborg University. I work here at the AAU Smart Lab, where I do research in robotics and in how robots are going to be used in the factories of the future. The lab is a lab where we investigate robots. So it's a multidisciplinary lab where we are focused on advanced robotics. with a special emphasis on manufacturing robots. We created the lab because we saw there was a big need for robots in industry. The industry is challenged by small batch sizes, by constantly introducing new products and so on. So there was a need for new robotic systems for manufacturing. We also saw a need for multidisciplinary research, and we found that having a physical lab, a place where we could meet, where researchers from various departments could meet and do research, was very useful for the research that we were doing. We have 4 focus areas. One of them is on industrial processes. So here we do research in particular on welding and on laser installation. Secondly, we are working with exoskeletons, or doing research on exoskeletons. The research here is aimed at giving people with limited mobility the option to walk or use the upper body for various tasks. Then we do research on AI, on self-learning and self-adaptive systems. A growing area where a lot of new technologies are coming out that we really can benefit for in the robotic world. One of the projects we have there is the Little Helper project, which is a project on a mobile robot which can help you doing a simple task in your manufacturing environment. And finally, we do research on robots in larger production systems. Here we have a special focus on the role that robots will play in Industry 4.0, that is the future of manufacturing. Most of the research we're doing here is done in collaboration with companies. They come with applications and we use them as specification for our research. We also have partners who are system integrators and who are building technology, so people who are building robots. And finally, we have a number of universities around the world where we collaborate. In the next couple of years, we want to investigate the possibility to build a swarm factory. That is a factory where the manufacturing equipment, including robots, are very, very simple, small machines that individually can do very simple tasks. But when we combine them, then intelligence will emerge, and we expect that we can design much more advanced and flexible systems than we have today.
Hello everyone, I'm Dimitris Chrysostomou, and in this segment I'm going to tell you more about our research in autonomous industrial mobile manipulators. As you may know, most industrial robots are fast, reliable and safe to use when they are behind protective fences. However, their mobility and flexibility is limited, as they have to be stationary, bolted to the ground and programmed for one task at a time. Almost a decade ago, here in the Robotics and Automation group of AAU, we developed a robot assistant which can coexist with users for safe and easy interaction. We call it Little Helper, our flagship research platform which we use to bring flexible solutions, easy to program and integrate into a variety of industrial tasks and scenarios. In collaboration with many industrial partners, we have developed different versions of our Little Helper research platform. It is a modular platform that consists of mobile or movable bases, while it can support 1 or 2 robotic manipulators. It adapts accordingly depending on the level of interaction we want to accomplish with our users. Sometimes we have to tackle tasks where we need to work away from users, executing everyday procedures such as delivery scenarios inside our smart production facility, where mobility, precise calibration, localization and mapping are very important. We also want to facilitate users who work in sensitive environments, where human presence should be limited. In these cases, we employ virtual reality and augmented reality techniques, which can provide a unique perspective of the working environment to the users, while they operate Little Helper from another room. Assembly of industrial parts is another area where we use Little Helper extensively. It is a very demanding task where advanced robot functionalities such as force feedback and station calibration are critical. In these cases, accurate object detection, recognition and grasping are very important as well. On top of everything, Little Helper is developed to enable non-expert users to use a robot in everyday industrial tasks. For that reason, it runs a skill-based programming interface in the background, which has been designed to facilitate easy and fast instruction of collaborative robots by inexperienced users, while it supports quick integration of existing off-the-shelf components in terms of hardware and software packages. Naturally, when we collaborate in close space with users, safety is a top priority in our research. Therefore, we have equipped Little Helper with user detection methods based on image processing and artificial laser walls. There, Lidi Helper can detect the user and adapt the speed of the robot arm, and it can communicate its current operating status with color-coded visual feedback. Finally, Lidi Helper is also the platform we use as basis for our future robotics research. Towards our vision for a more sustainable society, many of our current projects focus on assistive human-robot collaboration tasks for automated disassembly processes of electronics and industrial components. This way, we promote circular economy initiatives and reduce the environmental footprint of manufacturing industry. Stay with us, as Casper now will present our future research direction on swarm production, and later Simon will dive into our AI research in industrial robotics and manufacturing.
Thank you. I'm Casper Skov, and my primary research is within solutions for smart factories. Let me present to you our research on swarm production, which is a new upcoming research area where we combine the domain of swarm robotics with industrial manufacturing to achieve high flexibility on the shop floor. Here in our AAU 5G Smart Lab, we have established a smart factory environment, including a Festo CP factory production line, our many robots and little helpers, operator assistance tools, and not least a suite of digital solutions interconnecting these assets. In terms of flexibility, even this Industry 4.0 production is inherently constrained by the use of conveyors as they route products along fixed paths, limiting us to a sequential flow. With offset in this constraint, we are motivated by the vision of having products transported using cheap, small, mobile robots to create the production paradigm we call swarm production. Using mobile robots not only gives us large routing flexibility, but also makes the system more robust against failures, allows easy scaling of capacity, introduction of new processes without system downtime, and allows individual order flows and priorities. We imagine the swarm will be composed on a variety of different robots with different capabilities, ranging from small part-carrying robots to little helper-sized processing robots. Currently, we are carrying out early design sprints, experimenting with the layout and composition of both part-carrying robots and processing robots. To decrease the cost of the mobile robots, our architecture centralized the navigation and online route planning of each robot on a central edge cloud. Thus, fast, low latency and robust wireless communication is required between the robots and this edge cloud. For this, we have built up an infrastructure with both private and public 5G networks, Wi-Fi 6, and both an ultra-wideband and an ultrasonic positioning system. An infrastructure that allows reliable and low latency communication, even when using a swarm of devices. Finally, retaining production efficiency while exploiting this flexibility offered by swarm robotics calls for very frequent task plan updates. Together with our colleagues from computer science, we are working on distributed, near-optimal task planning and scheduling strategies using the AI technique called Q-learning. Some of these strategies we are currently testing out in large simulation environments, including hundreds of robots and a highly dynamic order flow. And now over to my colleague Simon, who's going to present much more in depth about our AI research.
Hi, my name is Simon Berg. In our next part of research, AI for industrial robotics and manufacturing, we are tackling the AI gap between research and industry, where we focus on adaptive and self-learning robots and automation systems. AI is redefining the landscape of intelligent robotics and automation in manufacturing industries. We help manufacturing companies navigate and demystify the hype around AI and put it into practice. We do this through student projects, research projects, and strategic collaborations with the companies. Let's have a look at some of our projects. Deep reinforcement learning is one of the pinnacles of AI today. In one of our projects, we work with robot grasping. How can we enable a robot to, on its own, learn how to grasp objects without knowing anything beforehand? The robot acts as an autonomous agent where it learns how to act optimally and carry out the task without any supervision from a human. Through the interaction with the object and the environment, it receives rewards, and over time it learns how to act in an optimal way. We also use this technique for mobile robot behavior and navigation. So how can mobile robots learn how to navigate a human environment in an optimal and safe way? Human-robot interaction is always critical in many robot applications. The natural interaction between the human and the robot we enable through natural language processing and acoustic analysis. we design and develop voice assistants so the human worker can naturally interact and talk to the robot. Through various commands, the robot learns how to carry out tasks that are given by the human worker. Acoustic analysis can also be used for other industrial processes, for instance robot welding. By recording the acoustic signals and time series data from the welding process, we can analyze and assess the quality. We also rely on computer vision in many of our robot applications. So a robot system or industrial task without eyes makes it very difficult to solve the task. In one of our projects, we detect defects on offshore platforms. This is usually a very tedious and dangerous task, which requires a lot of manpower, and in the end it becomes very costly because we have to send humans to the offshore platforms. By designing an automated system, we can detect certain defects and automate the maintenance process needed for these kind of industries. Finally, we want to enable artificial intelligence for the small and medium-sized enterprises. These days, we see that AI is primarily for the universities and larger companies who have the budgets and skills to actually carry out a deep learning project. Through one of our projects, we investigate how we can enable advanced technologies for the smaller companies so they can also harvest the benefits of artificial intelligence. In this case, we need to wrap the methodologies and models in an easy and intuitive platform which can enable the shop floor worker to actually train the network without knowing anything about deep learning. In this case, we want to be able to feed many different kinds of data inputs, which can be time series data, acoustic data, images, videos, and so on. So AI is a natural enabler for improving the manufacturing industry of the future. Our vision is to continue close collaboration with the industry and enable these technologies and make them accessible for both big and small companies.
Okay, thank you very much. This was our short presentation, and I think I'll leave the floor to you, Thomas.
Okay, thank you very much to the Advanced Industrial Robotics team. And just to remind the participants in this that there is a chance to ask questions for the teams in the chat function. If you don't ask questions there, you will have to listen to my questions. But I have a question for this group, and I'll start out. I noticed that you are very active in industrial collaboration, and maybe you can give us an insight into the steps that you take from you first engage with the company until you actually have a project up and running with a private industry. And also, if you could give us some examples on how that inspires your research.
Yeah, actually, there are several ways where we engage with companies. But I would say that the wish list that we have is that we usually start by getting or with the companies identifying a major challenge. So how do I? So with a large Danish company, for instance, could be how do I realize flexibility and efficiency at the same time, which is a major challenge. And then we engage in some. There's some fundamental research that we have to do. We introduce students and maybe also PhD students in that. And usually we have companies following the projects as it go along. Here in recent years, we have used we very much taking up the agile approach. So we would run frequently sprints together with the companies, something like every third month, and use these sprints where we build up physical demos as a measure of progress. And then at a certain point of time of this research, the company would say, or hopefully they'll say that here's something we can use. And then figure out how, or by themselves figuring out how this is implemented in their own industry.
Okay, so there's a few questions here, and the first one is on communications technology. What do you use 5G for today?
Kasper, can you answer that? Will you answer that?
Yes, I can do that. Thank you, Ole. So we are currently building up the infrastructure, but we have the 5G system in place. We are currently using it for communication between our little helpers and our production line. And we are going to use it also as the communication between all these swarm, tiny small swarm robots. We're also experimenting with making our smart production line that is currently wired, making each module wireless, which would facilitate much faster and more fluent reconfiguration.
Okay, thank you, Kasper. So this was a question from Christian Slette, and now there's a question from Kelvin Kolsø Nygaard, who asked that if you are doing swarm robotics, will you need to divide your production area so that humans are in one part and the swarm of robots in another part?
And this is actually an ongoing discussion. So initially we thought that this was only robots. But as we engage with some of our companies and try to sell this idea to them, they say, well, maybe we should have robots or humans there as well. And one approach could be simply treat us humans as part of the swarm. So and this is actually quite an interesting research area. I think that so how would we include humans or us humans and interact with this swarm of robots? So no, it will not be divided. Humans and robot will interact in some way, which we don't know yet.
So that there's a follow-up question here from Kelvin. Is that will the goal of the swarm manufacturing be the lights out black factory?
And the short answer is no.
No. Okay.
That's not the goal.
Then there's another question from Eski Karadas from Kværnland Group. Can you explain further which kind of projects do you have regarding the welding robot and welding quality inspection?
So maybe I can say something about what we do with welding robots, and then Simon can say something about the quality control we have. So at the moment, one of the projects, or one of the bigger projects we're running at the moment, is a project with where the aim is to automatic program welding robots based on a product configuration. So a lot of companies today, when you buy a product, you sit on a configurator and then you design the product, and then you get the shape and so on of your product. So what we are doing now is getting this, introducing on top of the underlying product model, process information, welding process information, which then can be transferred automatically into robot programs.
Okay, and then the welding quality?
Yes, Simon, will you say something about the...
Yeah, sure.
Yeah.
So we have ongoing research and student projects in this area, setting up the systems, gathering the data, and this is probably some of the biggest challenges in gathering the right data. We have a couple of companies involved in this right now who are very interested in these kind of techniques where we can do this sort of non-invasive and very low-cost quality inspection. So it's very much ongoing research, but already now we see huge potential in doing this kind of quality inspection from microphones and the acoustic data.
Okay, so thank you very much to the Advanced Robotics team. If you take your presentation down, then we move on to robots in art, and we have Elizabeth ready.
Yes. Hi, thanks so much. Thanks, Thomas, and I'd like to thank Henrik, our host, and the Danish Academic Society of Robotics for the invitation to speak with you about robots and art. I'm going to begin by showing a short video that highlights some of the research in our lab, and then I'll share some examples of some current research.
My name is Elizabeth Jochum, and I lead the Relate Research Laboratory for Art and Technology, housed here in the Faculty of Humanities. We're an interdisciplinary research group, and we have members from the technical faculty of IT and design, and we also collaborate and work on research projects with the engineering faculty in order to build bridges across our fields. in our lab, we research the connection between the visual and performing arts and existing and emerging technologies. And we research how to best integrate these new tools and practices into art making. So artists always use tools, whether it's a paintbrush or a musical instrument or a computer. And in our lab, we think of robots as tools for art making. So we want to see how robots can actually maybe contribute to generating new art forms. But we're also really interested in understanding how the arts can open up new perspectives and maybe even generate new solutions for robotics. All of the research that we do is grounded in a concrete problem from the real world. And we use artistic research and artistic methods in order to investigate that problem and come up with some possible solutions. So the example of the drawing robot, we are working with an industrial robotic arm, and we have programmed it to engage in a collaborative drawing task. Now, there's nothing really new or novel about programming a robot to draw, but instead what we're doing is we're looking at something a little bit different. So instead of thinking about a robot that only produces drawings, we're thinking about drawing as an activity that models a bunch of different type of behaviors and things that we're interested in when designing human-robot collaboration. So in human-robot teams and collaboration, you have to understand and have a really strong understanding of nonverbal communication, turn-taking, intentionality, shared workspace, shared goals, and the drawing activity becomes something that the human artist and the robot can do together. And so we use drawing as a model, really, for getting a better understanding of what's involved in human-robot collaboration. So it might seem strange at a moment in history when the world is facing some pretty serious problems globally to be focused on using new and advanced technologies to make art. But I'm convinced that the most pressing problems that the world faces today is not going to be solved through monodisciplines. All the latest discoveries and most important innovations have come from cross-disciplinarity, have come from people working across fields. And that's exactly what we're trying to facilitate in the Relate Lab.
So as I mentioned in the video, the Relate Lab is an interdisciplinary group of international researchers from several departments, from art, architecture, computer science, human-computer interaction, sound studies, dance, and media art. So we are truly multidisciplinary. We all work with technology, and we're united in our belief that collaboration is integral to innovation. And in particular, we think about robots as catalysts for innovation in art and design and vice versa. So if you, to that end, we actively collaborate with the wider research community on some of these workshops, symposia, and other public events at academic conferences. And if you've attended ICRA in the last few years, you might have noticed that they now regularly include robots in art as one of their featured forums. In 2018, we co-organized an ICRA workshop on soft robotics and art, and hosted an interactive art installation at the conference. Some of this work has been collected in a volume by Springer, which you see here, and is the topic of a forthcoming issue on creative approaches in HRI for frontiers in robotics and HRI. So one of the things we look at in our lab is robots and dance. And we know that if robots are going to be able to move in human environments, they're going to have to be able to move spontaneously and considerately around people. And this means being able to judge where people are going and what they want based on observations of how people move. So we invited professional dancers into our lab in order to study how they approach movement. Instead of thinking about designing motion trajectories and path planning as an engineering problem, we think more about it like a dancer might, as a choreography problem between people and robots. So here's a short clip from an improvised performance that we did at a theater festival in Aalborg.
Thank you.
So all of this was improvised. None of this was pre-scripted, and the dancer had only met the robot maybe 2 or 3 times before this and had never performed according to this kind of choreography. But the goal here is not to teach robots how to dance, and it's not about replicating specific dance styles. Instead, we're using dance improvisation as a bottom-up approach for thinking about embodied interaction, about what it means for robots and people to move spontaneously together. We're trying to get closer to that question of that swarm lab, I think, that Ole mentioned earlier. So another area we work on is dance and exoskeletons. And we've got a collaboration with the international artists Louis-Philippe Demer and Bill Vaughan from QUT in Brisbane and Concordia in Montreal. And their artwork Inferno is an interactive performance where audiences dance in exoskeletons during a 50-minute long performance. And during the performance, the exoskeletons are controlling the movement of the participants' upper limbs, but they are able to move around and dance together. And if this sounds strange, I've got a short video of what the performance actually looks like. So one of the things we learned from talking to our colleagues who work with exoskeletons for rehabilitation was how difficult it can be to design comfortable exoskeletons and motivate people on how to use them. We already heard from Lotte earlier about some of those human factors, those real challenges to exoskeleton adoption. But this artwork has audiences all over the world literally paying to have this experience for an hour where they're wearing a 12-kilo exoskeleton. And so I thought, okay, there's something here, right? We can explore this connection. And we're working together with the artists in order to develop new methods that combine dance and movement therapy with exoskeleton training and rehabilitation. And what we're finding is this approach has the added benefit that because it's a social activity, it also improves motivation and well-being, as well as the benefits of physical rehabilitation. Now, the last project I'm going to talk about is Heart. You saw some clips from the collaborative drawing robot you saw in the video. Last May, we received a grant from the Health Foundation to develop workshops for mental health patients in collaboration with the local government's Arts and Health Culture on Prescription program. Now, again, as I said, the goal here is not to make a robot draw, but it's rather to use drawing as an activity for studying human-robot interaction. And we want to use these drawing and painting workshops with mental health patients, both in the artist studio and in the lab, to identify which factors are most important for people when working alongside robots. And we hope to expand this work in other hospital settings with other populations in the context of other arts and health initiatives. So we're also exploring the connection between dance, drawing, and human-robot interaction and embodied activities in general that rely on technological interfaces. So here you see Valeria, our artist in residence, who is using a stylus to teleoperate the robot, and that is producing a drawing. And using the same technology, as you see in this video, she starts to use her body as a tool for controlling the robot's motions. And then using computer vision, we track her movements and generate new drawings, which are projected on the floor. So essentially, she can start performing. performed this at the National Museum of Science and Technology here in Denmark, which was the short clip you saw. And you can see that we're looking at dance as a form of both science communication to show how robots work, but also as a way to study the relationships between human environments, human bodies, visual tracking systems, and robots. So another aspect of our research in the lab is the critical and ethical study of new and emerging technologies. My colleague Morten Sonnegaard co-founded an international conference series titled Politics of the Machine, which critically examines how machines and other technologies are impacting culture and perception. And this is great because this is an example of interdisciplinary conference that bridges humanities and STS discourses with applied robotics research. And lastly, on a final note, we're also committed to developing new educational programs that train this kind of transdisciplinary thinking for both students and faculty. So AAU is leading a new Erasmus Plus strategic partnership project that links artificial biology, robotics, and art. We're working with Trento and Aalto and the ADIS Center for Advanced Design Research. And this project highlights the value of the interdisciplinary work that we do at AAU, and hopefully will lead to more collaboration across robots and art. So with that, my presentation is finished. You can find out more about our work that we do in Relate and at our website, and I'm happy to answer any questions that you may have.
Okay, thank you very much, Elizabeth. It's a fascinating insight into what robotics is also. It's not only engineering and science in the engineering area, but it also reaches into humanities. And there is a question for you, for Lazaros Nalpantidis, and he asks that a lot of the discussion takes place about the introduction of robotics and STEM in elementary school to elementary school kids. Have you considered your work within this scope?
Yeah, so actually one of the things we were doing at the, working with the museum this week was kind of doing some outreach and dissemination. It was interesting because the population at the Museum of Science and Technology is a lot of mostly children and young families. And a lot of their technologies, especially when children encounter robots in actual kind of industrial robots or manufacturing robots that they have on collection there, they're always necessarily, you know, behind gates, behind glass. And one of the things we're working with the museum and their programming is thinking about how we can design both more interactive exhibitions and also workshops that are really sort of hands-on and that provide those kind of experiences for elementary aged children. And there's a lot of really cool work happening by other colleagues of mine who are working more specifically in curriculum development. But I'm a big fan of not STEM, but STEAM, science, technology, engineering, arts, and math. And it's my mission to put that A in STEM.
And then there is a question for you here from Shopping By, and he asks, have you considered how artists and robots communicate with each other?
Yeah, it's funny because we deliberately work with artists who are quite curious about technology, but also who haven't had much exposure or much familiarity. And so it's lovely because when I work with engineers, they come to the technology with a set of preconceived ideas and notions about how this machine works, because they understand how it's programmed and they understand the systems logics behind it. Artists don't. They meet the machine as a co-creator. And so just at the outset, that is a different kind of template. It's a different beginning for a new kind of conversation. And with the drawing robot, you know, we can communicate through gesture. That's how artists communicate with one another. But you could also communicate through image, communicate through sound. So there's all sorts of different kind of multimodal aspects. I guess it depends on the artist, but the possibilities are infinite.
So maybe let me follow up a little bit on that, because we all know that working cross disciplines, it can be very inspiring, but it can also be very difficult. How do you keep, you're obviously very good at this, so how do you keep the motivation up with whoever participates in your work?
Yeah, well, it's a passion project for everybody. It has to be. But I think that's the thing that I found in all of the work and all the projects I've worked on is people might, in that new meeting, in that interdisciplinary work, the work might be contained within a specific project or specific assignment, but the thing that I find more often than not, it actually transforms how people think about their own work in their home discipline. So coming into a workshop with an artist or doing a workshop for even just a couple of hours and being exposed to these other ideas, they stick with you. They carry with you into your other applied work that you do in your own discipline. It's transformative in that way. So it's easy to stay. It is difficult, but it's also easy to stay inspired. I believe in it.
Okay, thank you very much to Elisabeth. And let's move on to the final presentation, and that is a presentation on human-robot interaction. So if you would please, Matthias,
yes,
take control.
You, Thomas. It's a bit hard after these inspiring videos to continue, but I would like to stress the interdisciplinarity. I think that's a really important topic we need to discuss and work with, and I think the university needs to find some good institutional settings for supporting that so that it becomes easier. But that's a different discussion, so I will present what we do in the HRI lab, and like most of the other groups, we have produced 4 short videos, one that introduces the lab as such, and then we talk about human-robot trust, about deep learning in HRI, and the last one will be about socially assistive robotics. So let me share my screen, and then I hope you enjoy the videos. My name is Matthias Rehm. I'm a professor for human-machine interaction here at Aalborg University, and I'm also the coordinator of the Human-Robot Interaction Lab here at Aalborg University.
Please calm down.
The lab was founded as a strategic research initiative by the university, and the idea was to bring together different perspectives on human-robot interaction. And I think we're at a unique position in the Danish research landscape because we have these 5 institutes that collaborate in this lab. And that's computer science, we have electronic systems in, we have media technology in, techno-anthropology, and we also have communication and psychology now associated with this lab, so we also have this humanistic perspective.
Great. You look happy.
We focus on human factors in human-robot interaction, and that means we have quite different approaches and methods we look at. We run traditional experimental setups where we investigate specific interaction behavior, but we also started to look at the more big picture, so what is it actually that a user wants from a robotic system, and there we work a lot with healthcare institutions where we go in, talk with the staff, talk with, for instance, the residents in an elder care center to find out which kind of robotic technology makes sense in their daily life or in their work life, and then start developing the systems with them.
I'm happy too.
Currently, we're in the lucky position that our research seems to be very interesting also for others. So, for instance, we are currently starting up a new EU project where we will be leading the HRI research in this project, and which brings together different industries across Europe. So that's a very nice setup for us.
Did I miss something?
I think the work that we're doing is extremely relevant and important currently, because we see that robots move out of their restricted environments, for instance on the factory floor, and they come into more dynamic, more social environments. And that happens in industry, where we have the collaborative robots coming up now, but it also happens in more social settings, in healthcare, in rehabilitation and so on. And if we want to make this work with people, then we need to look at these human factors that we are focusing on. Trust in human-robot interaction is becoming more and more relevant with robots moving into dynamic and social environments. We can see that, for example, with collaborative robots in industrial settings or with social robots in care or educational contexts like museums. Trust becomes important because it determines the success of the deployment of the robotic system. It has been clearly shown that trusting a system not enough leads to suboptimal use of the system. Trusting the system too much, on the other hand, can have hazardous consequences both for material or even human lives. For example, when the system is not monitored appropriately. Thus, ensuring that the user or operator has an appropriate level of trust is key for the utilization of a robot. The challenges are now twofold. We do not know how to measure trust in the interaction, for example, by observing the user. And we do not know how we can manipulate trust in the interaction. In the following, we are going to present two studies that look into these two aspects. Trust is a multidimensional concept based on characteristics of the task, the environment, the human operator, and the robot. Current trust measures are, though, mostly post-hoc questionnaires that measure the subjective impression of the user's trust towards the robot. While this can serve as a kind of ground truth, it does not help us to regulate trust in an ongoing interaction. Instead, we need to be able to correlate observable interaction behavior to the user's trust level in order to prevent over or under trust in the system. Potential trust indicators are, for example, body postures and movements or physiological measures like GSR or heart rate variability. In our experiments on close proximity collaboration, we are controlling most of the above-mentioned characteristics to be able to relate trust measurements and observable behavior. We can see how the changes in the robot's operating speed, for example, but also in the robot's placement or the task itself influence behavior and trust measurements. One additional challenge is that we do not know yet which behavior of the robot or which type of error breaks trust. So in another series of experiments, we started to look into the elicitation of specific levels of trust. In this study, Pepper serves as an instructor in a building task. We looked at two variables, a robot that recognizes the user's task behavior correctly versus one that has recognition errors. The second variable was a robot that gave correct instructions versus one that gave incorrect instructions. Results show that we are able to control the user's level of trust by these manipulations, which now allows us to examine in a principled way the relation between trust, robot behavior, and observable user characteristics. For successful interaction, we have to face at least two challenges. We need to make sense of the input from the user and the environment, and we need to react appropriately to this input. Both challenges are often data-driven and thus require AI and machine learning to tackle them. In this video, we are going to present some of the work where we use AI techniques, looking into social navigation in the built environment, intention recognition in close proximity interaction, and maybe the most challenging one, effective interaction with citizens with brain damage. Guiding visitors through the built environment, for example at airports, shopping malls or museums, is an interesting challenge. While there has been progress in analyzing static group configurations and avoiding collisions with them when moving through dynamic environments, we know not much about the dynamics of the groups themselves when they move through the built environment. To create this knowledge, we work on two angles: analyzing human group behavior and running experiments including guiding robots in lab and field situations. The data is then used to train a model for social navigation. In our work on collaborative meat processing, we are investigating pre-movement prediction, making use of eye gaze tracking. By analyzing the dynamics of the operator's gaze behavior during a task, we are able to predict which object in the workspace the operator will be reaching for next. Results of the first explorative studies are promising. Experiments were due to Corona run in VR, making use of a Pupil Labs eye tracker and HTC Vive. With 3 objects in the workspace, we were able to predict half a second before any action happened
which object the user will work on next with 80% accuracy. Prediction rates at 1 second lie around 60%. The current prediction is based purely on the eye gaze data without any consideration of the task context. So the next series of experiments thus aims at making this prediction more robust by integrating this contextual knowledge. Affective states play a crucial role in stroke rehabilitation, but citizens are often missing the possibility to express their emotions due to motor or cognitive challenges. Thus, we engaged in a project with the Regional Neurocenter to develop a pseudo model for effect recognition that could then be used for monitoring rehabilitation sessions and engaging in motivational interactions with a social robot. In our model, we have employed a linear combination of convolutional neural networks and long short-term memory networks. The CNNs extract the facial features from the facial input data of citizens with traumatic brain injury, and the LSTM then exploits the temporal relation on the basis of the extracted features. The first field study at the Neurocenter before the corona lockdown showed that Pepper can be used as a motivational tool when supplied with the effect recognition system. Institutional care has been described as a promising sector for the application of socially assistive robots, for example as companions for older people, reminding them about activities of daily living or of taking their medicine. It has also been shown that the development of these robots has been dominated by technical challenges and is often based on assumptions or stereotypes about the target group. This impression was also confirmed by the institutional stakeholders that we interact with. As a consequence, we decided to take a strong user perspective into account and created an interdisciplinary team consisting of engineers, ethnographers, designers, care personnel, and of course the primary users. We call this research strategy From Social Practice to Social Robots, with the main argument that we need to focus on the practices around the tasks that we want to automate to be able to integrate and not only disrupt the work and living routines in the institutional setting. The different disciplines contribute to this research strategy by their own methods and research questions or their best practice guidelines. Our research process usually starts with an ethnographic study where all team members participate to study care practices in context. Result of the ethnographic study is a preliminary project catalog that is further developed during workshops with staff and potential users, which serves two purposes: collect valuable contextual information as well as ensuring that staff and users become also project owners for the following development process. Having decided on the general project idea, we start the co-creation process with the user, where we in a series of workshops develop design and functionality of the robot, starting with simple drawings over cardboard models to first working prototypes. When the whole team has converged on a viable solution, we then start producing the robot at our own workshops, making use of current maker technologies like laser cutting and 3D printing. The finished product is then deployed and further tested in context, leading more often than not to further iterations. Is this a scalable approach for robot development? Maybe not, but it allowed us to gain insights into the practices surrounding assistive robot technology in institutional care, especially in regard to interactions with special needs users. The three main results from this project are a complex process model for reminding processes in institutional care that informs the further development of socially assistive robots. A new interaction model for institutional settings, moving from classical dialogical interaction to interaction with several users with different participation roles. And last but not least, a proof of concept for user-driven modular robot development.
Yes, thank you very much. So if you want to visit us virtually, you can do that in 2 weeks' time. There are still places for this event by Digital Lead Denmark, or you can have a look at our LinkedIn channel or website.
Okay, thank you very much, Matthias. There is a question for you from Christian Sled, and he says, cool. Have you tried to interpret worker gestures in an industrial context yet?
Worker gestures?
Yes.
Well, we have this project with Danish Crown and DMRI where we look at collaborative meat processing, and there we still focus on this trust issue, right? So gestures or body movements in that respect, we just look at with this specific perspective on what does it tell us about the trust level of the user. But yes, gestures or body movements would also be part of that.
Okay, I have a question. I think it's well known, and I think you mentioned some things around this, but it's well known that long-term meaningful interaction is one of the problems in human-robot interaction. What is your take on that? What have you done in your research to address that?
I would totally agree. That is one problem, and one problem might be that there is not a very good application yet where we need to have this long-term interaction. But we actually look at several aspects of that. So with the effect recognition, we want to get more engaging interactions and look at motivational cues that we can use in the interaction. We have another project currently running with Honda Research Institute in Japan. They are interested in bringing a new tabletop social robot to the market. And there also one aspect is how can we keep this robot engaging over a longer time. And there from our perspective, again, we look at social cues that we find in interaction. How can we keep it interesting? How can we keep it surprising even after you have interacted with the system for maybe 2 months? Yep.
Okay. Thank you very much. I think to preserve a little bit the time, I think we should, if you take your presentation off the screen, then
yes,
we will move back to the final part of today's program. And I'll give the word to Henrik.
Thank you, Thomas. That was a very inspiring trip of what's going on in Aalborg, and you can see sort of the breadth of what's going on. You can also see that there's a lot of it's very diverse, it's very collaborative, it's an amazing place. If you have questions, we would love to, if you have for any of the speakers, we still have a little bit of time so where we can entertain questions for them, whether it's about their study model or the different research, or how do they collaborate with all of these wonderful partners. So I'll break for 10 seconds here to see if we have any sort of last minute questions before we wrap it up. And while I do that, I can sort of, while I'm waiting for this, Thomas already mentioned at the beginning, if you go to robotics.aau.dk, you can basically find sort of a list of all the different groups and all of this. So that would sort of help you find sort of further information about this. Other than that, I think this was really inspiring, very happy. We hope to see you again before too long. So you can see here, Aalborg has December 9th, a workshop, their own workshop, and where you can go and actually see. I assume it's still going to be a virtual workshop, given that even Denmark is impacted by COVID. But also in about 4 weeks, we will have, which was sort of what Thomas was pointing to, in about 4 weeks, we will have a workshop in Copenhagen, at the capital in Lyngby, at the Danish Technical University, hosted by Ole Madsen, and where we will talk more about sort of the third big cluster of robotics in Denmark. So we're very much looking forward to that. And then, as I said, December 16th, we will have the final workshop where we'll be talking about why is it that Denmark is so incredibly successful at translating technology from these academic institutions into real world applications. So thank you very much. You can see here an email address for how you can connect with all of these researchers in Aalborg, how you can access links to the various research groups. And on top of this, if you didn't have a chance to see the entire thing, you can go back to the Danish academic research group and get there, or society, and get the YouTube channel, both from the video that was from a month ago from Southern Danish University. The videos from today will be uploaded, and there will be more information. So thank you for joining us. Stay safe out there.
Yes, also thank you for me, for to all that joined, and thank you very much to my colleagues who gave us this insight into the work on robotics in Aalborg. And I have to say that there are other groups in the university, part of robotics, Aalborg Robotics, that were not able to participate today because we had to respect the time limitation. But please visit us at robotics.aau.dk, and when this COVID-19 is over, please come to Aalborg and see us. And please reach out to the participants today if you have any questions following up on this. So that concludes the webinar today.